Imagine you're looking at like one of those ancient Japanese baskets, those beautiful woven ones. With that pattern, it's called Kagome, right? Well, that pattern, it's inspiring some serious cutting edge physics. Like we're talking Kagome magnets, and they have this intricate lattice like structure that's got like everyone in the physics world buzzing. And hold on, there's more. A team at Rice University, they just dropped the study in Nature Communications, and it's seriously turning our whole understanding of these magnets upside down. So basically, we're going to break down this kind of complex physics paper and see how it could, change things like quantum computing and all that superconductor stuff. Ready for the twist. These magnets are behaving in ways no one ever expected. So they zeroed in on these thin films made of iron and tin, or FES-10, I guess. Why choose that combo?
Well, you see, FES-N, it forms this very specific Kagome lattice structure, and it's not that hard to make thin films with it. And that's really important because to really get a good look at the material's electronic structure, you need a super thin, pure sample.
Oh, I see. It's kind of like when you need a thin slice of a rock to look at it under a microscope, right? But how do you even see electrons in something that tiny?
They use these, well, pretty awesome techniques, I guess you could say. Molecular beam epitaxy and angle-resolved photoemission spectroscopy. Basically, they build these super thin films, almost like atom by atom, and then use this special light to knock electrons off the surface. And by looking at those electrons, they can map out how the electrons are acting inside the material.
Wow, so it's like they're playing microscopic billiards with light, just knocking those electrons around.
Yeah, that's actually a really good analogy. So going into this, scientists thought the magnetism in these materials was all about the electrons. They're just, zipping around freely, mobile electrons. But that's not what they found.
Wait, really? So what's actually happening then?
Okay, so what the Rice team found is that the magnetism in FES-N is driven by electrons that are basically stuck, in specific spots. We call them localized electrons. It might seem like a small thing, but it really changes everything.
Okay, I think we need to unpack this whole localized versus mobile electron thing. Why does it matter so much if an electron is zipping around or, stuck in one place?
Okay, think about it this way. Imagine a city, a busy city, with delivery trucks zooming around, bringing stuff everywhere. Those are like your mobile electrons carrying that electrical current and contributing to magnetism. But now imagine all those trucks are just parked, all lined up in a pattern. Those are your localized electrons. They're still there, but they're not moving around freely. And that changes the whole dynamic of the city, right?
I like that. It's a great way to visualize it. So instead of electrons zipping around like those delivery trucks, they're parked in specific spots, and that's what's creating the magnetism in FES-L.
Exactly. And one of the big clues for this is something called Kagome Flatbands. Think of them like special zones inside the material where the electrons have very specific ways they can behave. The study found that these flatbands in FES-N were split even when it was really hot. And that's a big sign that localized electrons are the ones responsible for the magnetism.
Hold on. So even when things heat up, these localized electrons just stay put and keep that magnetic influence.
Yeah, they're way more stable than we initially thought. And it gets even more interesting. They also found something called selective band renormalization in FES.
Okay, that one sounds pretty complex. What does that even mean?
Okay, imagine a party, right? And there are all these different groups of people having conversations. Some are talking quietly, some are having these intense debates. Well, in FES, some electrons are interacting way more strongly with each other than others, and that's impacting how the whole material behaves. It's like those groups having those intense debates, they're driving the energy of the whole party.
So it's not just that the electrons are parked, it's that some of them are having these really focused interactions, and that's what's influencing the magnetism.
Exactly. And the thing is, this selective band renormalization, it's been seen before, but in iron-based superconductors, which makes this whole thing even more interesting.
It's like we're finding this hidden connection between these magnets and superconductors, and it all comes down to these parked, intensely interacting electrons.
You got it. And what makes this discovery so groundbreaking is that it totally changes our understanding of how Kagome magnets work. It's opening up this whole new path for research, and it could have some really huge implications.
Okay, now I'm really hooked. So we've established that this study is shaking things up, but what does it actually mean for things like, quantum computing or superconductors?
Well, imagine if you could build a quantum computer that's way more powerful and stable than anything we have now. Or a world where we can send electricity with almost no energy loss thanks to high temperature superconductors. This discovery could be a major step towards those goals.
Now you're talking. But how exactly does this discovery about localized electrons in Fessesen connect to, like, these futuristic technologies?
Well, let's start with quantum computing, okay? One of the big challenges we have now is creating stable quantum bits, those qubits. Think of them like the building blocks of quantum computers. And there's this really promising approach called topological quantum computation.
Whoa, topological quantum computation sounds kind of like Star Trek stuff. Can you break that down for me?
Yeah, it's pretty mind-bending stuff, to be honest. It uses the interplay of magnetism and those special flat bands we were talking about before to create super stable quantum states. And guess what? Kagome magnets, with their unique electronic properties, they look like perfect candidates for this type of quantum computing.
So if we can figure out how to control these localized electrons in Kagome magnets, we might be able to build super strong qubits for these next-gen computers.
Exactly, and that's just the start. The implications for high-temperature superconductors, they're just as exciting.
Superconductors, those are already pretty amazing, right? Conducting electricity with zero resistance. But from what I understand, they usually need these like crazy low temperatures, which makes them pretty impractical for most applications. How could this research help us get closer to those high-temperature superconductors that everyone's been looking for?
Well, it turns out that the same kind of electron behavior we're seeing in these Kagome magnets, those localized electrons with strong interactions, well, those are also believed to be involved in high-temperature superconductivity.
So by understanding how these parked electrons interact with each other in Kagome magnets, we might unlock the key to creating superconductors that work at much warmer temperatures.
Exactly. Imagine a world with lossless power grids, crazy efficient electronics, even levitating trains. That's the potential of high-temperature superconductors.
Sounds like something out of a sci-fi movie. But it could actually become reality thanks to this deeper understanding of these tiny localized electrons. It's wild how a seemingly small difference in electron behavior could totally revolutionize these huge fields.
Totally. And what's even more exciting is that we're just scratching the surface here. This discovery is opening up a whole bunch of new avenues for research.
So where do we go from here? What are the next steps for scientists working on this?
Well, one of the big questions is whether other materials might act the same way. Is this just an iron tin thing, or is there a whole group of materials out there with these parked electron properties?
Right, because if this is happening in other materials, it opens up even more possibilities for tech advancements.
Exactly. And the researchers are going to be digging deeper into how this all works, the specific mechanisms. Like, how are these localized electrons interacting? What role do those flat bands play? We still have a lot to figure out.
It's like we've opened this door to a whole new world of physics, and we're just starting to explore it.
Yeah, and that's what makes this discovery so cool. It's not just about finding answers, it's about asking even more interesting questions.
I love that. So what does all this mean for, the person listening? Why should they care about these tiny electrons and their surprising behavior?
Well, I think the biggest takeaway is that it shows how powerful fundamental research can be. Sometimes the most groundbreaking discoveries come from just exploring the unknown, from questioning what we think we already know. And who knows, maybe this research will lead to technologies that change our lives in ways we can't even imagine right now.
Right. It's a good reminder that there's so much we don't know, and that looking for knowledge can lead to incredible breakthroughs.
Absolutely. And that's the beauty of science. It's a journey of exploration and discovery that never ends. This study is a perfect example of how that journey can lead to unexpected and truly amazing results.
We've talked about quantum computing and superconductors, but are there any other areas where this discovery could have an impact?
Definitely. Anytime you have such a big change in how we understand things, it can have effects in a lot of different fields.
Yeah.
For example, this research could help us develop brand new materials with specific magnetic and electronic properties.
So we could be talking about things like more efficient solar panels or next-gen data storage devices.
It's definitely possible. The key is to keep asking questions and keep pushing the boundaries of what we know.
That's why I love doing these deep dives. They remind us that there's always something new to discover, always another layer to uncover. And sometimes those discoveries have the power to change the world.
And it all starts with the willingness to explore, to dive into the unknown, and embrace the wonders of science.
Well said. I think we've covered a lot today. It's kind of crazy. We started by looking at an ancient Japanese basket weaving pattern, that Kagome lattice, and now we're talking about revolutionizing quantum computers and superconductors.
I know, right? It's amazing how looking at something as simple as a pattern can lead to these like huge scientific discoveries. This whole journey from a basket to cutting-edge physics, it really shows you how everything's connected.
Totally. And the biggest surprise for me was finding out it's those localized electrons, not the ones moving around freely, that are driving the magnetism in these Kagome magnets. That one little detail could change so much in so many fields.
It really could.
Hmm.
And it just goes to show how important it is to keep questioning what we think we know and pushing the limits of our knowledge. Sometimes the biggest breakthroughs come from challenging the way we think things work.
So, as we wrap up our deep dive into the world of Kagome magnets and those surprising parked electrons, I have one last question for you and for everyone listening. What other materials out there could have these hidden properties? What other scientific truths are just waiting to be, like, challenged and maybe even proven wrong?
That's what's so great about science. It's a never-ending exploration. There's always something new to find, another mystery to solve. This study is really just the beginning of a whole new area of research, and who knows what amazing discoveries are waiting for us. It's up to all of us to keep asking questions, keep exploring, and push the limits of what we know.
I couldn't have said it better myself. So, to everyone listening, stay curious and be open to the unexpected. The next big scientific revolution could be hiding anywhere. And that's a wrap for our deep dive into Kagome magnets. Thanks for joining us, and we'll see you next time.